Hello everyone, welcome to our talk at the CVPR 2021. We will talk about our study on radar camera fusion via representation learning in autonomous driving. As a formulation of the radar camera fusion problem, we are given a camera image and a bunch of detected vehicle 2D bounding boxes and a bunch of radar pins. Our goal is to make the associations between the 2D bounding boxes and the radar pins if they correspond to the same vehicle in the scene. The desired association relationships are highlighted as red lines in the image. There are three features to note about our method. First, our method is an object-level fusion method, as opposed to other data-level fusion or feature-level fusion methods. Hence, our method is more amenable to real autonomous driving systems. Second, our method is a learning-based method. Compared to traditional rule-based radar camera fusion methods, our method is less susceptible to performance degradation in challenging scenarios or failure in corner cases. Third, most existing learning-based radar camera fusion methods rely on LiDAR to provide ground truth information. Yet, our method adopts a traditional radar camera fusion methods to automatically generate association ground truth, entirely eliminating the need for LiDAR. Our method is based on representation learning. The input features include the raw camera RGB image, the bounding box features, and the radar pin features. We aim at learning representations of each 2D bounding box and each radar pin. Here is an overview of our method. We first use the bounding boxes and the radar pins to create a pseudo image, where each feature occupies one image channel, and each bounding box and radar pin has a unique pixel location. Then we concatenate the pseudo image with a raw camera RGB image to form a final pseudo image to be fed into a neural network to perform representation learning. At the last layer of the network feature map, we extract the learned representations for each bounding box and each radar pin at its pixel location. During the training, if one bounding box and one radar pin are associated, we pull together their representations. Otherwise, we push apart their representations. In this way, the association relationships between bounding boxes and the radar pins are encoded as the Euclidean distance between their representation vectors. During inference, we first calculate the affinity matrix between representations of bounding boxes and the representations of radar pins. Then we select the best associated bounding box for each radar pin by looking for the minimum distance. We also designed two mechanisms to enhance performance. First is the loss sampling. To mitigate the labeling noise, we first filter low confidence positive pairs in the ground truth and sample the negative pairs for loss calculation. Second is the ordinal loss. We observe that the relative ordering of the Y-max of bounding boxes reflects the ordering of the depth of the object in 3D world. Hence, we can enforce the self-consistency among the ordering of the bounding boxes and the ordering of the associated radar pins. We encode the self-consistency as the ordinal loss and add the loss into the final loss function during training. Here are some quantitative results. For loss sampling, we studied the different sample ratio, and the performance gain is 1.1% in terms of the F1 score. For the ordinal loss, the performance gain is 1.8% in terms of the F1 score. Lastly, even though we use the traditional rule-based algorithm to generate ground truth label during the training, our proposed learning-based algorithm significantly outperforms the rule-based teacher by 11.6% in terms of the F1 score. Here are two examples of the predicted associations. Despite multiple big trucks present in both examples, our proposed algorithm correctly predicted their associations. On the other hand, in the second example, there are two bounding boxes incorrectly associated. The mistakes are largely due to small sizes of the object in the camera image and also the heavy occlusion. Thank you for your attention. Please refer to our paper for further details.